Welcome back, ladies and gentlemen. In this video, we're looking at applying our graphing skills to this idea of accelerated motion for an object that is experiencing accelerated motion, not constant motion. So why graph this kind of stuff? Well, you've seen this before. There's a lot of information that can be contained in one graph. And also, and you'll see this, we're going to be able to bridge between what we observe when we can record data and the equations, and we can see that the equations seem to really come from the graph. The equations are sort of naturally there in what's already happening, and the graph lets us develop some of these equations. You'll see that. So for an object that is speeding up, we have some object and we tracked it for 5 seconds, and we watched its velocity go from 10 meters per second to 35 meters per second. It looks like it's 5 meters per second faster, and 5 and 5 and 5 and 5 meters per second faster each time. Okay. And we're going to graph this. We have the data, we're going to graph it. And I have the graph here, and you can see the independent variable on the horizontal axis down here, and the dependent variable on the vertical axis here. And so we have a velocity time graph. That's how you'll hear this called, and we're going to analyze these a bunch. It's going to be really cool, and actually it's going to get pretty easy for you. You'll see. But notice that the velocity did not start at 0, so the graph doesn't start at 0 velocity. You have to put a data point there, and we plot our data points. All right. And ignore the red for just a moment. Let's look at this. So clearly you can see this is linear, and that's pretty important, even though it doesn't exactly, that line of best fit doesn't touch every data point exactly. You know that it doesn't have to. With linear, we're going to look at the slope. It's a guarantee. And so the slope, you remember, is rise divided by run, rise over run. So our rise is a change in velocity, a delta v. And our run, here on the graph, is a change in time, delta t. And when we do rise divided by run, we do delta v divided by delta t. Rise divided by run, delta v divided by delta t. Well, you know already that that is equal to acceleration. So this is really, really important. This is a huge idea. On a velocity time graph, the slope of the graph tells you the acceleration. The slope of a VT graph tells you the acceleration. That's real important. We can look at this, so we break up the velocity, final minus initial, break up the time, final minus initial. Velocity final was 35 meters per second. Velocity initial was 10 meters per second. Time final is 5, and initial is 0. So 35 minus 10 gets us 25, and 5 minus 0 is 5. So 25 divided by 5, we get 5 meters per second. Remember that those units combine a little bit into 5 meters per second squared. This is the acceleration of this object. Its velocity is increasing by 5 meters per second every second. But so being able to work the math is one thing, and yes, you should be comfortable with that. But you must also remember the idea that the graph we made came from just, we observed an object. It might have been Mrs. Kangaroo, and maybe she was really booking. She was really hauling because it was, I don't know, there was a new opening movie at the theater. Who can say? But from the data, we graph the data. And from the graph, we get an equation and some knowledge. This isn't just coming out of thin air. This isn't just some esoteric thing that nobody can understand. This is actually easily understood. This, what acceleration means, and where we can see the mathematical acceleration straight out of the graph, that came from the real life observations. And that's real important to remember. But there's more. There's always more, of course. We're looking at some really interesting stuff here. The graph tells us the rate of acceleration when we're looking at a velocity time graph. But the graph tells us more. And now, see, that was the blue matching the blue here. We're going to look at the red matching the red here. And I have a simple sketch to kind of draw your attention to that. The area under the line. Now, what line am I talking about? I'm talking about this line on the graph. The area underneath that line. Actual surface area on the paper, right? It can be broken up. In this case, it's pretty simple. You have this triangle here, and you have this rectangle here. I just labeled them area 1 and area 2. And the areas of basic shapes like rectangles and triangles is very easy to understand. But what's interesting is the area under the line is going to tell us Well, what's delta x again? That's right, delta x is displacement, change in position. How far does this object travel in that amount of time? From a velocity time graph, we can tell how far it goes. And technically, we'll use the word displacement. Okay, so that is displacement. Area number 1 is a rectangle. So we're going to look at the displacement is equal to area 1 plus area 2. We have to add the two areas together. Area 1 is a rectangle, where it's going to do base times height, or length times width if you prefer. But the triangle, area 2, well, the area of a triangle is 1/2 base times height. So here's a triangle, there's our base, and there's our height. And we'll take half of that. So in this case, what is base times height of the rectangle? Well, it's initial velocity times the time. And you can see that here in the graph. The height of this rectangle is the initial velocity of 10 meters per second. And we're going to multiply by the base, which is 5 seconds right here. Okay, so initial velocity times time. And the triangle, well, we have 1/2 base times height. The base is the time. So the triangle has a base here, and it's just the time. And what is the height of the triangle? The height is a change in velocity. So the height of the triangle, from there to there. So you take the initial and the final, and so you need the change is that length right there. And that's what we look at. So we have this kind of initial equation we could use. It's not usually represented in this sort of, with this look though. And the reason why is it's very often handy to have an equation for displacement, not with an initial velocity and a change of velocity, but with an acceleration in the equation. We know this object is accelerating. We know the speed is not constant. We can see that from 1 second to another, the speed has changed. And so we'd like to have the acceleration in our equation. Recall this relationship, that change of velocity is equal to acceleration times time. And this is basically coming from the previous equation, the second equation of motion, just rearranged it a little bit. But when I take this substitution of acceleration times time and I put it in place here for delta v, and I work some of the algebra, and I basically simplified it this. And this becomes our third equation of motion. The displacement of an object that's accelerating is equal to initial velocity times time plus 1/2 times acceleration times time squared. It's real important to note that there are no parentheses used around this term, and therefore that exponent is only being applied to time. Time is the only thing being squared here. That's it. So, to sum this up, the area under the line of a VT graph tells you the displacement. And recall that the slope of a VT graph tells you the acceleration. So from one VT graph, you can learn two very important things, the acceleration and the displacement. Thanks for watching. I'll catch you next time.